All right, guys, today we're going to talk about applying properties of rational exponents. And so some of this is going to be new, some of this is going to be familiar to you, some of this you may have seen in Algebra 1, some of this is going to be completely new. So we'll go through it, we'll do some practice, we'll see some examples, and hopefully we'll all make some forward progress. All right, so let's get started. Starting off, our section header here is that we are going to apply properties of rational exponents. Okay, so there's our header. And so the properties of rational exponents is what we can do with the exponents beyond just changing them from rational form to radical form. So when we look at a product, that means multiplication. So we can take, here we go, a to the m, and if we multiply it by another that has the exact same base but can have a different exponent, we're just going to keep the base the same and then add the exponents. Okay, so number example, numbers usually help us here. So we come in here and go 2 to the third times 2 to the fourth, and that's going to give us 2 to the seventh. Works the same with variables. X to the third times x to the ninth, and that can give us x to the 12th. Okay, you can see how that works. Now, if we're talking about a power, what we're saying is that we have an exponent to an exponent. So again, we'll start with a to the m, or a to the n here. And if we take that to the power of m, what we end up doing is we're just multiplying those two exponents together. So we get a to the mn, or m times n. So with a number here, we can see that this would be 3 squared to the fourth, and that would become 3 to the eighth. Okay, so we're just multiplying those exponents, exponent to an exponent, we multiply. Okay, we can distribute over exponents. So let's come in here, we take a and b, so now we have two bases, and we're multiplying those together, and we're going to distribute the m as our exponent. And so this becomes a to the m times b to the m. So we can distribute exponents over multiplication. So we can see how this works with another example. X, y, so there's your two bases. To the sixth, we can rewrite this as x to the sixth, y to the sixth. All right, so we can see that we can distribute over multiplication. Please note, we cannot distribute over addition. Okay, we can only distribute over multiplication, so just watch that. I've seen plenty of students make that mistake over the years. All right, we can have negative exponents, a to the negative m. If we have that negative exponent there, that means that we're going to take the reciprocal, so we get 1 over a to the positive m. So when we take that negative exponent, we take the reciprocal and have a positive exponent. So with numbers, we would have 4 to the negative fifth. That can become 1 over 4 to the fifth. All right. We have the quotient property, which says that if we are dividing two exponents, so we have x to the m, or sorry, a to the m over a to the n, we're going to subtract those exponents, a to the m minus n. So as an example here, we can take a look at this. We go x to the third divided by x to the 1. This would equal x squared, because you've got 3 minus 1. Another example here, if we take x squared and divide it by x to the 9th, that would give us 1 over x to the 7th. Or visibly we could write that as x to the negative 7, but we would never leave that exponent as a negative. We're always going to write that as a positive exponent, so which is why I left that as 1 over x to the 7th. And then finally we have distribution over division, so quotient distribution. So we can come in here and we would say I have a and b, so that's not multiplication, that's division, and I have the exponent m, and we can write this as a to the m over b to the m. Okay, so if we come in here and look at this with numbers, we could say we have 2/3, and we take that to the 4th. We can rewrite that as 2 to the 4th over 3 to the 4th. Okay, so there's your basic exponent properties, and we're going to use that in all sorts of contexts with rational exponents. We also have some properties of radicals, so square roots, cube roots, and such. So let's go ahead and take a look at that. So properties of radicals. We have the product property. So the product property basically says that if we have an nth root, so that could be a square root, a cube root, any type of radical, a times b on the inside, we can write this as the nth root of a times the nth root of b. So we can just separate that multiplication on the inside and turn it into 2 separate radicals. And that can be helpful sometimes when we're evaluating or solving, so that we can take each part and treat it separately. So let's look at this example. Here we go. We have 3, 2 times 4. And so we can actually separate this out and say, okay, so let's go the cube root of 2 times the cube root of 4. All right, so there's a nice clean example. Not terribly useful in this case, but you can see how it works. We can also do the same thing with a quotient. Our quotient means division. So if we have the nth root and we have a divided by b, we can write that as the nth root of a divided by the nth root of b. Okay, doing this with numbers. Here we go. We have the 5th root. Again, it doesn't matter what we're talking about. This works for all radicals. The 5th root of 1/9, and we could write that as the 5th root of 1 divided by the 5th root of 9. Okay, so applying that property, being able to change the form is sometimes going to be useful depending on what type of problem we're trying to solve. All right, so let's look at some examples of what that looks like. So please note that if you're going to be able to do this, the indices, plural of index, the indices must be identical. That means the same, identical. Must be identical when you're multiplying. Okay, so taking a look here, I have the cube root of 12 times the cube root of 18. So I can rewrite this as the cube root of 12 times 18. Just merging those two together. And then I can combine, so let's do a little factoring real quick. If we take this factoring here, we go 2 times 2 times 3. That's the prime factors of 12. And 18, we have 2 times 3 times 3. So if I want to now take the cube root, I'm looking for groups of 3. So I have 3 2's, so that gives me a 2. And I have 3 3's, so that gives me a 3. And so the cube root of 12 times 18 is just going to be 6. Now, notice that I did not multiply 12 times 18. When I did this, that would just be extra work. I'm going to factor it anyway, so it makes a whole lot more sense just to factor it right away and not multiply that all the way out. All right, let's do another example here. I have the fourth root of 80 divided by the fourth root of 5. They have the same index, so they're both fourth roots. So I can go ahead and rewrite this as the fourth root of 80 over 5. Here I am going to simplify that. That's going to give me the fourth root of 16. And then think through, okay, what is 16 is 2 times 2, 2 times 2 times 2 times 2, right? And then that means that the fourth root of 16 is just 2. All right, now let's look at an example with variables. A little more intimidating, but still just as doable. We have multiplication, so we're going to be able to combine some parts of this together. The 5 out front, we're going to leave out front. And when we multiply this out, so we're going to have 5 times the cube root of 100 times 10. We're going to group our numbers times 10, and then group the variables. A squared times a gives us a to the third. We know that 100 is 10 times 10. And so because we're looking for cube roots, we know that we're looking for powers of 3. So we're looking for 3 when we're looking for our groups. So we have the 5 that was our constant out front. Then we have 3 groups of 10. So we have 3 10s there. So that becomes a 10 out front. And then we have a to the third. And so the cube root is the inverse of a to the third. So that undoes that a cubed and gives us just a. So our final answer is just 5 times 10 times a, or 50a. Let's look at another example here. We have 6 times 3 out front as our constants. So we'll just write that first, 6 times 3. And then we'll take our cube root, and we're going to have our numbers 9 and 24. We're going to gather those at the front so that we can factor them easily. And then we have n squared times n, so that's going to be n cubed. And now we'll go ahead and factor our 9 and 24. 9 we all know is 3 times 3. 24 is going to be 2 times 2 times 2 times 3. Okay, so our cube root is again telling us that we need groups of 3. So we have our 6 times 3 that we had from before. We have 3 2's, so we'll have a 2 out front. We'll have 3 3's, so we'll have a 3 out front. And then we have n to the third, and so if we take n to the third and take the cube root of that, that just gives us n. And so now when we multiply this together, we do 6 times 3 times 2 times 3 again, and we get 108 n. All right, we're going to go ahead and continue by adding and subtracting like radicals. the first thing that we need to realize is that we need both the same, must have the same index, must have the same index, and we also need the same radicand, meaning the number inside the radical. Okay, so the radical needs to be identical, but the coefficients do not matter. So those coefficients do not matter as far as, oh, that's not a no. Let's try that again. Doesn't matter. There we go. All right, so if we take a look at this, we have the cube, 3 cube roots of 10 plus 2 cube roots of 10. So if we look at this using the distributive property, we can see that we could like factor out that cube root of 10, and we would get 3 plus 2 times the cube root of 10, meaning we can just add 3 plus 2, giving us 5 cube roots of 10. So we can really think of this radical as a unit that we can just add 3 cube roots of 10 plus 2 cubes root of 10 is going to give us 5 cube roots of 10. So we look at this next example. Here we have, there's an invisible 1 out front, 1 cube root square root of 9x minus 6 square roots of 9x. And so we can look at this as, well, 1 minus 6 times the square root of 9x. That's going to give you negative 5 square root 9x. So we really can just add or subtract those coefficients when the radicals match. Okay, let's look at another one here. C here, we can see they don't actually match right now, but the question is can we make them match? Well, if we simplify that square root of 12 first, that's going to be 2 root 3, because we have square root of 4 times the square root of 3. And so that gives us 4 root 3 plus 2 root 3. 4 plus 2 is 6. And the root 3 there is just telling us how many is what we have 6 of. So we had 4 root 3s plus 2 root 3s, which gives us 6 root 3s. Okay, look here at D. None of these 3 match, so we can't add them unless we can make the index and the radicand match. Unless we can make that radical fully match, we can't add or subtract them. So we'll go ahead and simplify this first. We go, all right, root 12 is 2 root 3. We just did that one. Square root of 48 gives us 4 root 3. And the square root of 27 is 3 root 3. So here we have the square root of 3 as the common index radicand. So that's the common radical that we can have. And so we can just go ahead and go 2 plus 4 minus 3 times the square root of 3. 2 plus 4 is 6, minus 3 is 3. So this equals 3 root 3. So that messy expression right there can simplify down all the way to just 3 root 3. All right. We can also simplify radicals even when they have complex variables. What we're going to see here is that we can separate this and look at it pretty easily as just the number and the variable. So let's separate those two here. We go, okay, so I have the cube root of 27. 27 is 3 times 3 times 3. Which means that when I take the cube root of 27, I just have 3. Now, we've also talked about the fact that the cube root undoes something cubed. So the cube root of x to the third is just going to be x. The y squared here, we don't have 3 of them. And so because we don't have 3 of them, those are going to have to stay behind inside the radical. So we're going to have the cube root, and we're going to have y squared that has to stay inside. And then when we look at the z to the 6th, when we have z to the 6th here, we're going to realize, okay, so I have one group of 3, so z to the 3rd times z to the 3rd. So that means I actually have 2 separate expressions here that I can take z to the 3rd and take the cube root of it, so that'll give me z squared here out front. And so when I just write this all cleaned up, I take out that multiplication. It's just 3x z squared cube root of y squared. All right, let's see if we can do that again here. Looking at the 4th root of 32 times x to the 5th, y to the 4th, z to the 2nd. So looking here, we're going to take the 32, and we're going to turn it into 2 to the 5th. And if we realize that that's 2 to the 5th, we're going to have one group of 4 that we can pull out. There's a 2. And we're going to have inside the radical a 2 left over because we had 5 of them. So 4 of them make the 2 for the coefficient out front, and then 1 left over is going to stay inside the radicand. Then we're going to go ahead and take away a group of 4 from x to the 5th, which means we'll have an x out, and we'll have 1x left over because there were 5 of them. 5 minus 1 gives you 4. 5 minus 4 gives you 1, so we have 1 left on the inside. And then we have z squared. Y to the 4th first. Let's deal with the y to the 4th. We have 4 of them, which means we can pull that y out. Nothing left over, so nothing stays inside. And the z squared, there's only 2 of them, so both of them have to stay inside. The rule was we needed 4 of them. We only had 2, so all of those z's stay inside. And there's our simplified expression. Okay, so as long as we're taking this chunk by chunk and following the rule of the index, which is we need 4 of them in this case, simplifying these expressions isn't too bad. All right, last one of these types of problems. We have the square root of 20, x to the 5th, y to the 9th. And so if we take 20, we're going to break this up and go, oh, this is just 2 times 5. I have a pair of 2's, so I know that I'm going to have 2 on the outside. Inside the square root, I'm going to have 5 left behind. When I look at the x's, I can take 2 groups of 2 out of that, which leaves me x squared up front. 1 left over on the inside, which gives me x. I have y to the 9th, which means I'm going to have 4 groups of y's that I can take out with 1 y left over. And there is my simplified expression, as simplified as I can get those. Okay, so let's take the same idea of simplifying radicals with variables, but this time instead of treating it just as radicals, let's look at what we can do when we simplify these things and want to deal with them as rational exponents. Okay, so our goal when we're simplifying rational exponents is to make sure that we have no radicals in the denominator and we want no negative exponents. Okay, so that's our goal when we finish simplifying these expressions. Now, we're starting off here. We have x to the 1/5 times x to the 3/5. We know that multiplication tells us that we're going to add. So we're going to have x to the 1/5 plus 3/5. And all of you can very clearly be able to do that math. It's x to the 4/5. So that's pretty simple there. When we have multiplication, we can just add those radicals there. When we look here at the next one, b, we have exponents multiplied together and to a power. So let's deal with that power to a power first, which means we're going to distribute. So we'll have 5 to the 1/3 to the 3rd times 7 to the 1/4 to the third, which is going to give us, when we simplify that, 5 to the 3/3, because remember, when an exponent to an exponent we multiply, times 7 to the 3/4, and 5 to the 3/3. Well, that's 3/3 is just 1. So when we simplify this down one more time, we just get 5 to the 1, which is just 5, times 7 to the 3/4. So we can use those exponent properties to clean these expressions up. With C, again, we have the same base. We're able to multiply these two expressions, which means we're going to add the exponents. So we just get y to the 5/7, just adding 1/7 plus 4/7 and getting 5/7. Okay. This next one here, we have division. So we'll take 10 divided by 10 to the 2/5. What we need to remember is that when we have 10, there's a 1 written there that we don't normally write because we're good mathematicians and don't write things unless we have to. So for us to add or subtract these, we need a common denominator, so that radical needs to match. So we're going to rewrite this as 10 to the 5/5 over 10 to the 2/5. Now we can use that quotient property where we're allowed to subtract, which is going to give us 5/5 minus 2/5, which will give us 10 to the 3/5. All right, that gives us a pretty straightforward example there. So as a rule of thumb, whenever we're simplifying, we're going to start with the exponents. And end with the exponents. We're going to start with radicals and then we'd end with radicals. So what I mean by that, guys, is if the problem gives you exponents, even if you convert the problem to radicals to solve it, you should end with exponents. So whatever you start with, if it's exponents, end with exponents as your final answer. If you start with radicals, you should end with radicals. Whatever you start with in the problem, that should be what you finish with, because that's the form of the problem, unless it tells you otherwise, of course. The last thing is while you're simplifying, it is absolutely okay to go back and forth. Okay, sometimes it'll be easier to work with an exponent, sometimes it'll be easier to work with a radical, but while you're working through the problem, you can absolutely go back and forth, but just make sure you end with whatever the form was that you were given. Okay, so when we're simplifying, we're going to use conjugates. We'll talk about that in a second video. We're going to make sure that we have the same base when we're simplifying, and we're going to use our exponent rules. Power to a power or power times a power are the two that we're going to use most often, and so that gives us a good place to start with, and we'll finish this up next time.